Okay, so we've seen a couple of these. Here's a tensor. Think about them as numbers if you want. But what do you notice about this particular tensor? So everything in this corner is basically mirrored in this corner. So this is what's called a symmetric tensor. And a symmetric tensor means that I flip the indices and I get the same thing. So for example, you know, A1, 3 in this case, so 1, 3 is kappa. And that's also equal to A3, 1. And we can also have antisymmetric tensors. What's true about antisymmetric tensors? And there are actually a couple of things you could say. So I think this is, you know, start with definition. What's true about BJK?
It's not equal to BKJ.
Yes, something more specific. So anti is the exact opposite of.
What was it? KJ. BKJ. Yeah. No.
So symmetric, positive. So flip the indices 1, 3, and 3, 1. I get the exact same thing. Antisymmetric is the opposite of that, where BJK is equal to negative BKJ. Okay, as a consequence of this, so for example, we'll get there when we write something down. What needs to be true about the diagonal elements of an antisymmetric tensor?
Not negative of the other one.
Yeah, like let's say that I put a 1 here or something like that. Does 1 equal negative 1?
Inverse. Taking guesses.
Yeah, what's the only number that equals the opposite of itself?
0.
0. Okay, until you guys get into quantum field theory and you learn about Grassmann numbers. But yeah, so this needs to be true, is that the diagonals of these need to be 0, because the only way for like B, you know, 2, 2 to be equal to negative B2, 2, the only number that, you know, is the negative of itself implies it's 0. Okay, but then off the off diagonals, then we can have some fun stuff. So we could have some number there, no restriction, but then this would be minus omega minus kappa and minus tau. Okay. So this is maybe like a linear algebra definition. If we want to go into higher order tensors, we don't have to have fully symmetric or fully antisymmetric tensors. They can just be symmetric or antisymmetric around 2 indices. So I'll just say certain pairs of indices. And there are like physics implications of that. So for instance, you know, if you're thinking about 3D at the surface of Earth, is that we have some symmetries, whereas, you know, as far as gravity is concerned, what we call the X and the Y directions are treated evenly, but the Z direction is not. The Z direction is where we're being, you know, pulled downwards. So if I wanted to express something having to do with strains of gravity, it might be symmetric around the X and Y axes, but not symmetric around the X and Z axis, for instance. So you don't have to be fully symmetric. You can be symmetric around, you know, particular pairs of indices. So expanding that definition, what we can say is that if I have some T alpha, beta, gamma, delta, so if we're symmetric on the first and third index, that means that T alpha, beta, I don't know why I did gamma, delta, is equal to alpha, delta, gamma, beta, which is to say, I just flip the first and the, wait, is it first? Yeah, sorry, thinking in GR. First and third indices, so gamma, beta, alpha, delta. So flip 1 and 3, I get the exact same thing back. Likewise, I could be anti-symmetric in the first and third indices, which means if I flip those, I get the opposite of the thing back. Okay. So that's generically true. We could be symmetric on the first and third index. We could be anti-symmetric on the second and fourth index. We could be symmetric on the first and third index and anti-symmetric on the first and second index. So this is, once you get into higher order tensors, this is just a statement about pairs and not the whole thing. So before leaving that, however, and this is an important note, is that you can, for a second rank tensor, so you can express the whole thing in the same way that you can take any function at all and express it as an even and an odd part. You can take second rank tensor and you can symmetrize and anti-symmetrize it. So let's say I have Tij. I can express that as a symmetric part plus an anti-symmetric part. And I forget this is homework or if it was kind of like too boring to be homework, but this is how you would do that. So the symmetric part, you just explicitly make it symmetric. Tij plus half Tji. And then the anti-symmetric part, you just make it anti-symmetric. Yeah, I think that's the proof right there, because you can explicitly show that this is symmetric and show that that's anti-symmetric. And then when you add them up, clearly the Ji piece goes away, but the Tij piece stays, which is what you wanted in the first place. Okay, so only true for second rank tensors. Okay, so it's kind of a side note. We want to go back and do some house cleaning. And if I were to give you a little piece of advice, like what aren't tensors? Basically, the work's been done for you sociologically in the physics textbook, is that if it's got units, it's probably a tensor. If it's got no units, you should be suspicious. It's not to say no, but you should be at least suspicious. So go back to our old friend, the Kronecker delta symbol. And the Kronecker delta symbol, delta, is delta ij. It's 1 if they're equal, if 0 if they're not equal. It turns out, and we'll prove this in, we'll see, how much time do we have? Yeah, we'll prove this probably the last thing we do. Turns out this is a tensor. So this is what's called an isotropic tensor. So this passes the test. There's another thing. So in a sense, this thing is for dot products, the delta, Kronecker delta symbol, and this thing is for cross products. So there's what seems like it might be a third rank tensor, which would let you put two vectors in, so one with an I index, one with a J index, and get a independent vector out, one with a K index. This is, it's called the totally anti-symmetric symbol. And we'll define it in a second. Turns out this is not a tensor, but it's like pretty close. So Levi-Citiva symbol is, you can think about it as a way of expressing cross products in Einstein summation notation, has the following property. So Eijk is equal to 1, -1, or 0. So it's 0 if there are any repeated indices. It's 1 if Ijk is a cyclic permutation. Of 1, 2, 3, which is to say the order is preserved. And it's -1 if an odd permutation occurs. Okay, so as a couple of examples, Levi-Citiva symbol 1, 2, 3 is equal to 1, because the 1, the 2, and the 3 wrapping around occur in the same order. Okay, that was way too easy. Levi-Citiva symbol 1, 2, 2 equals 0 because there are two 2's. 2 of any index is repeated. Okay, Levi-Citiva symbol 3, 1, 2 is equal to 1 because 1, 2, 3 occurs in the right order, just wrapping around. What about 3, 2, 1? What's Levi-Citiva symbol 3, 2, 1? So there's no way for me to rotate this and keep the order that I was given, 3, 2, 1, 2, 1, 3, 1, 3, 2, in which they appear in order. So that's what's called an odd permutation. So that's -1. Okay, what about Levi-Citiva symbol 1, 3, 2? What's that? So cycling this through, I get 1, 3, 2, 3, 2, 1, 2, 1, 3. At no point do I get the 1, 2, 3 order. So that's an odd permutation, 0. And finally, what's Levi-Citiva symbol 3, 3, 3? Definitely have some repeated indices, so that's 0. Okay, why are you doing this to us? Because you can do this. So Levi-Citiva symbol is a really nice way when you're expressing things in, for instance, Einstein notation or as tensors, can express the cross product really easily. And you're probably used to it by now, but appreciate how annoying writing a cross product is. So cross product, is the determinant thing in general. But I want to take B cross C, and I just want the ith component. It turns out that this is how I would do that. Levi-Citiva symbol IJK. B, J, J, C, K. Okay, so we have repeated indices. We have a K upstairs and downstairs, Einstein summation, and then upstairs and downstairs, J, Einstein summation. So we'll go through this one and see that it's correct. Okay, so I'll just write out all of the possible permutations. How many possible permutations are there of, possible triplets of IJK? So whoever's like pretty good at combinatorics, let me know. So overall, I have possibly 3 times 3 times 3, 27 of these. The good news is most of them are 0, so I'm not even going to bother. The only ones that aren't 0 are 1, 2, 3, and it's even permutations, 3, 1, 2, and 2, 3, 1. And then let me flip 2 of those, and I get the odd permutations. Let's do 2, 1, 3, and then just cycle that. 1, 3, 2, and then just cycle that. 3, 2, 1. Okay, so lots of zeros, but then we get a couple of non-zeros. And then this would be, because we only care about, for instance, well, let me just, write them down. So then we have B2, C3, B1, C2, B3, C1. And then I want to just pick on this one, so we'll just put the ones out there. B3, C2. And you can fill in the rest, but let me just pick on, let's find out what, like, for instance, the ith component, the first component is of this new thing. We'll say that A, define this to be A. So for instance, what is A1? Well, A1 would be, I pick out the 1 parts of these, so that and that. Okay, what's E1, 2, 3, B2, that's A1 is equal to, what's Levi-Citiva symbol 1, 2, 3? So that's an even permutation. So it's just already in 1, 2, 3. So that's +1. And then this is B2, C3. And then this is an odd permutation. So that's a -1. And then this is B3, C2. Let me put in X, Y, and Z so this looks more familiar. So this is saying AX is equal to B, putting everything downstairs like we're used to, BY, CZ minus BZ, CY. Does that look like a cross product? It is the cross product. And then you can look at the other 2 pairs and you can get the other 2 parts. So the 3 part and the 3 part, and then the 2 part and the 2 part. So this really is the cross product. And the way it works is it throws away all the repeated indices. So you get all of the even and odd permutations, and it puts a minus sign in front of the odd ones, just like you guys did manually with the determinant notation. Okay. So turns out if we want to embed cross products, which are really crazy things. I mean, if you remember that rule the first time you learned it, and just like, why is this? It's nice to have it expressed in terms of a thing that has like some simple properties. Okay. Which also means that if we can use Levi-Citiva symbol to express the determinant, or sorry, the, getting ahead of myself, the curl, is also possible, and the determinant is also possible. So cross product, curl, and determinant all have that same kind of mathematical structure. So this is the curl. And this is the determinant. Actually, see if you guys can write down the expression for, just pick one and try it. Remember Einstein notation and then upstairs, downstairs. And if you can get any of these, that's pretty impressive. So Levi-Citiva symbol is like the weirdest of all of the things we're going to get. Okay, so the curl of a vector field, and just like we did up here, it's easier to just say like this is the ith component. So I have v is a function of x, y, and z. Curl of v. Let's just look at the ith component. I have the ijk, and then I have d by d xj acting on v. Okay. And so the role again of the Levi-Citiva symbol is it makes all of the repeated indices 0, and it picks out the permutations and put the minus sign in where they need to be. And then finally, the determinant of a matrix can be expressed with the Levi-Citiva symbol. And this is kind of neat because what sort of mathematical object is a determinant, and what sort of mathematical object is rank? Oh, the matrix is a rank 2 tensor in this case. If the matrix is a rank 2 tensor, what sort of mathematical object should the determinant be? Also rank 2 tensor, vector, scalar. So that's got to be a scalar. So this is a little bit funky. So essentially what you're doing when you're taking a determinant is you're taking, if you think about what it is and you think about the formula for a second, you're kind of taking a cross product of the vector with itself in the second and third rows, and then you're dot producting it with the first row. So we need 3 copies of this, A1, I, A, 2, J, A, 3, K. So this is kind of leveraging our formula for the cross product. But the point is Levi-Citiva symbol is cool. All of those weird symmetric, anti-symmetric things we can express with it. Because it expresses the cross product, do you think this is going to translate like a good rank 3 tensor should? No. So it turns out to be a near miss. And it turns out that the Levi-Citiva symbol is a rank 3 isotropic pseudo tensor, which is a great piece of jargon. Okay, so any questions about that? We've got like 10 minutes, so I think that's enough time to go through how you would maybe prove some of these things. Okay, so we'll do this just to finish today. So a little bit of terminology and just kind of stylistically how you would prove some of this stuff. So you know about rank. So isotropic from a physicist standpoint, isotropic means same in every direction. from a mathematician standpoint, what that means is invariant under rotations. Okay, so this is important because you'll be asked if something's isotropic, you know, maybe you're a cosmologist and you want to see if your data actually obeys the cosmological principle or the or is invariant under rotation. So that's the mathematical statement of what you're really looking for, and we actually know how to prove stuff. And then secondly, pseudo tensor. So it transforms properly under rotations, but if I reflect from a left-handed to a right-handed coordinate system and my pseudo tensor is changed, then that's, or my tensor like object is changed, it's a pseudo tensor. So we really, you know, there's not much to talk about with pseudo tensors. Levi-Citiva symbol is it, as far as you guys will be exposed to, but showing something's isotropic I think is worthwhile. So let's do that and call it a day. So let's say we want to do this, because this is important. I stated it. Which is to say, let's upgrade our friend, the Kronecker delta symbol. So we have some complex number alpha from a symbol into a full realized tensor. So alpha delta, and then, yeah, let's just leave them downstairs, JK. So, which is to say any multiple of the Kronecker delta symbol is a tensor. And the way that alpha delta would look in actual units would just be like alpha, alpha, alpha. Okay, this isn't like a stunning proof because you look at this and you're like, yeah, totally, it treats every direction the same. It's just alphas in each of the three directions. But the point is, this is how I would prove it. So I have a thing that I claim is an isotropic second rank tensor. Generically, what do I need to do to get my second rank suspected tensor from its old basis into a new basis? So when I rotate a second rank tensor, what is it that I need to do? Okay, let me ask in a different way. And I'm playing fast and loose with the upstairs downstairs thing. We'll get to that at the end of the week. Is this okay? So I'll just take one rotation. I have a rank 2 tensor. I actually need how many copies of my rotation matrix?
2.
2. And I've got to make sure that the indices work out right. So I want to compute the following. All I know is that these things, the R's, obey the correct rules for rotations. So we'll call it K alpha and J beta. You really shouldn't mix Greek and Latin, but you know, it just makes everything look nice. Okay, so there's implied Einstein summation, but the thing is, this is really wonderful in Einstein summation notation, is like these are just numbers. They're like arbitrary numbers, each individual set of alpha, beta, J, and K you choose. So first thing I'll do is I'll just take like alpha out of there. And actually alpha is a really terrible choice because we already have an alpha. So let's turn this into a gamma. Can turn that into a gamma pretty easy. Yeah, not the worst thing ever, but kind of bad. Okay, and I can also use distributive properties if I need to. Like maybe I want to group the matrices together because I know certain things about reflection matrices or rotation matrices. But to be honest, I really don't need that, because what's true about the Kronecker delta symbol? Eventually, this is kind of how you think about it, is in the same way, and honestly, like the Dirac delta is a really great mnemonic for this, especially because you guys are probably working on those problems now. So the delta function picks out just a value at A, right? So this is almost our operational definition. In kind of a discrete way, it's, it's like finite dimension, infinite, but countably infinite dimensional cousin. The Kronecker delta can do the same thing. So let's say that I have some matrix or vector or something like that. I'll just pick on a vector. And the Kronecker delta can be, k can go to infinity. So let's say I have some vector vk and I have some delta k3 or something like that, right? So this would be kind of the equivalent state. This just picks out v3. It's kind of clear how the Kronecker delta works. Okay, let's say I just didn't tell you exactly that it was 3. Let's say I just said it was like j, whatever, that's just j. So in essence, what is this summation doing? This summation is just summing over k, and it until what's true. K is equal to j. So in this summation, what I get is the following: alpha r beta j, and then this summation, the summation over k implied by the upstairs downstairs repeated index, it was 0 until k equals j. And so what I have is r gamma j. Okay. And now I have properties of the rotation matrices themselves that tell me the following, is that this is equal to Kronecker delta gamma beta. So first thing we got from just the definition of the Kronecker delta, and the second thing we get from properties of rotation matrices, that this is actually equal to Kronecker delta beta gamma. Okay, so up to the change in indices, which is what we wanted, we put this in, we put alpha delta jk in, and we got alpha delta beta gamma out. So we rotated the thing properly, we got out what we wanted. This is still something that looks exactly the same. It looks like alpha along all of the diagonal components. So this is in fact isotropic, or rotation invariant. Okay. And I got a little bit sloppy with the upstairs downstairs indices in kind of a critical way, and we'll talk about that on Thursday, where really what I should have done is put an extra step in this argument that this really is an Einstein summation because the j can go upstairs and it's repeated. But we'll fix that when we talk about the metric on Thursday. So any questions on any of that? So that's kind of style of proof with implied summation notation.